Welcome to this explainer. Today, we're diving into the mind-bending, microscopic reality that makes up, well, absolutely everything you can touch, see, and feel. Seriously, from the screen right in front of you to the very air you're breathing, we're going to explore the hidden architecture of the universe.
Let's kick things off with a simple, everyday mystery. Why is it that you can build a massive, towering castle out of sand, but the second you try to stack water, it just slips right through your fingers? It flattens right out. It seems super obvious to us, right? But the scientific reason behind this behavior actually unlocks the deepest secrets of matter.
Think about kids exploring a riverbank, picking up pebbles. Those pebbles were broken down from massive mountains over centuries of erosion. We know rivers grind rocks into smaller and smaller stones, eventually making all that sand and clay. But we gotta ask ourselves, how far down can things actually be broken? Is a tiny grain of sand really the end of the line?
Section 1. Building blocks of everything.
So to see what happens when we break the world down into its absolute smallest pieces, imagine holding just a simple, everyday stick of chalk in your hand. It feels completely solid, unified, whole. To your naked eye, it's just one continuous object.
Now imagine snapping that chalk in half, then taking a mortar and pestle and really grinding it down. You're left with a pile of incredibly fine powder. But here's the thing. If you look closely through a magnifying glass, every single tiny speck is still just a piece of chalk. It hasn't magically morphed into a brand new chemical substance. Its physical size has just been drastically reduced.
If we kept up this grinding process forever, and assuming we had magical microscopic vision, we'd eventually hit a wall, a stage where the chalk literally cannot be broken down any further. These tiny final units are the basic building blocks, and we call them constituent particles. Basically, one whole piece of chalk is just an army of millions and millions of these constituent particles holding on to each other.
Section 2. The vanishing sugar mystery.
We know solids are made of these tiny particles, but let's see what happens when we mix things up a bit. Picture this. You fill a glass with drinking water, and you stir in 2 teaspoons of sugar. As you mix it, those solid grains seem to just vanish right before your eyes. Gone. Yet, if you take a sip from the very top, your taste buds will tell you that sweetness is absolutely still there.
So where on earth did it go? The sugar didn't just magically cease to exist. Instead, when it dissolved, millions of its constituent particles separated. And here is the secret. They essentially found hiding spots in the tiny, empty gaps that naturally exist between the water particles. We call these gaps interparticle spaces. The very fact that sugar can literally hide inside water proves that matter isn't just one solid block. It's made of distinct particles, with actual spaces between them.
Section 3. Forces that shape matter.
So what keeps a piece of chalk from just spontaneously falling apart into microscopic dust? Well, interestingly enough, long before modern microscopes were ever a thing, an ancient Indian philosopher named Acharya Kanad beautifully deduced this entire invisible reality. He figured out that matter must be made of extremely tiny, indivisible, eternal particles. He called them Parmanu and documented this whole foundational idea in a text known as the Vaisheshika Sutras.
What actually binds Kanad's Parmanu, these constituent particles, together are interparticle attractions. You can think of them as these invisible forces constantly pulling the particles close to one another. And the strength of this microscopic grip, it's the ultimate rule maker. It dictates everything about whether a substance is going to be rock hard, squishy and soft, or completely invisible to us.
Section 4. Solids. Tightly packed.
Think about hammering a tough iron nail, or maybe a block of wood. It resists your strike because its constituent particles are locked in this tight, unyielding embrace. In a solid, these attractive forces are so overwhelmingly strong that the particles simply cannot move past each other freely. They're trapped in fixed positions. The absolute only movement they're allowed is a slight, completely invisible to and fro vibration. And that right there is exactly why solids maintain a definite shape and a definite volume.
But what happens if we turn up the heat? When you heat a solid, you're injecting pure energy into that tight embrace. The particles absorb all that energy and start vibrating more and more violently. Eventually, the vibrations get so incredibly intense that the particles physically break free of those rigid positions. The attraction weakens and bam, the rigid solid suddenly collapses and melts into a liquid.
This actually perfectly illustrates that not all grips are created equal. Just think about melting points for a second. Ice has relatively weak attractions. It gives up and melts at just 0 degrees Celsius. Urea holds on until about 133 degrees. But iron?
Iron fiercely maintains its solid shape until it hits a blistering 1538 degrees Celsius. Basically, the hotter a substance needs to be to melt, the stronger that interparticle attraction is.
Section 5. Liquids, flowing shapeshifters.
Okay, so once those strong bonds are weakened by heat, the particles are still close, but the attraction has loosened up just enough to give them some freedom. They can now slide and glide past one another in this constant fluid tango. That's why if you pour 200 milliliters of water from a tall, thin glass into a wide, shallow bowl, it instantly takes the shape of the new container, or even the shape of your cupped hands. But, and this is crucial, it remains exactly 200 milliliters. Liquids have no fixed shape, but they absolutely maintain a fixed volume.
Now let's keep adding heat. When a liquid finally reaches its boiling point, that smooth, fluid tango turns into an absolute chaotic frenzy. The particles are moving so fast, so vigorously, that they break their bonds entirely. They just fly apart from one another, escape the surface of the liquid, and rocket right into the air as vapor.
Section 6. Gases, unbound and invisible. That dramatic escape brings us to the ultimate free spirits of the microscopic world. At this gas stage, the interparticle attraction is practically zero. It's negligible. Because nothing is holding them back anymore, gas particles just bounce around with endless energy in every possible direction. Like, if you light an incense stick inside an upside-down jar, the smoke doesn't just sit at the bottom, right? It rapidly spreads to fill every single inch of the available space. Because of this totally unbound freedom, gases have zero fixed shape and no fixed volume whatsoever.
So, to quickly summarize our whole journey here, we can see exactly how the simple rules of interparticle attraction completely dictate our physical reality. If the particles hold on with incredible strength, boom, you get a solid with a fixed shape and volume. If they loosen up just enough to slide past each other, you've got a liquid that flows. And if they break completely free, you get a gas that just constantly expands.
I want to leave you with this final kind of mind-bending thought before we wrap up. We've learned that even in a rock-hard solid, the constituent particles are forever locked in a state of invisible vibration. So, if even the heaviest mountain, the hardest diamond, and literally the device you're watching this on are all secretly buzzing with vibrating microscopic particles, is anything in our universe ever truly still? Thanks so much for joining me on this explainer, and definitely keep questioning the invisible world around you.